In this session, we will consider the normal distribution. There's actually an infinite family of random variables which are normally distributed. We first consider one that's called the standard normal. Okay, so in the standard normal, the PDF and the traditional notation for the standard normal is capital letter Z. So the PDF is of the form 1 over root 2 pi exponential minus 1/2 Z squared. Okay. And the expectation for the standard normal is 0, and the variance for the standard normal is 1. We'll get back to moment generating functions later in the course if we have time. Now, the other normally distributed random variables have PDFs like this. If X is normally distributed with expectation mu and standard deviation sigma, then its PDF, its probability density function, is 1 over root 2 pi sigma squared exponential minus 1/2 x minus mu over sigma squared. And you can see that if in the case of the standard normal, sigma squared and sigma are equal to 1 and mu is equal to 0, and if you put those values in, this would default back to the standard normal. Okay. We need a way, for what we're going to do later, we need a way to convert from a given general standard normal, sorry, a given normally distributed random variable X, which might have different mu and variance, and we have to convert it to the standard normal. We do it this way. We take X, we subtract off its expectation, and we divide by its standard deviation. And then the new variable that you get is in fact the standard normal. It will also be normally distributed just like X, except now its expectation will be 0 and its variance will be 1. Okay, now the reason we do this is we need to be able to calculate things like the probability that X takes values between A and B. Okay. Now doing the calculations is it's difficult to do. You can't do them using sort of standard common functions. And so what we do is we tabulate values for the standard normal, and then you need to be able to convert from your normal random variable to the standard normal variable. Okay, so the way we do it is this, what we did before. We subtract off the expectation of X and we divide by we subtract off the expectation of X and we divide by the standard deviation. So the probability of A less than or equal to X less than or equal to B is the probability of A minus mu over sigma is less than X minus mu over sigma, which turns it into the standard normal random variable, which is less than or equal to B minus mu over sigma. So now there are tables available, which will help us do the calculation for the right-hand side. Okay, so remember, what is this? This is given by the CDF, the cumulative distribution function. Okay, so this over here would be this probability is the cumulative distribution for B minus mu over sigma minus the cumulative distribution evaluated at A minus mu over sigma. Okay, and these can be found in tables. Those values for the CDF can be found in tables, or they can be found in, or they can be done online. Okay, sometimes the tables don't give the values for the for negative arguments. Okay, and the way you would do it then, if you had such a table and it doesn't give you the values for negative arguments, well, it turns out that f sub z of minus z, employing the symmetry of the bell curve, f sub z of minus z is equal to 1 minus f sub z of z. Okay. So that means that the probability that z is less than or equal to minus x is equal to the probability that z is greater than or equal to x. Okay, so now let's just do it. Let's use the normal random variable to do a problem. So supposing that you have a normal random variable and it's normally distributed with an expectation 100 and a standard deviation 10, what is the probability that it takes values between 80 and 85? Okay, well, the probability that x takes values between 80 and 85, now convert to the standard normal. It's the probability that x minus mu over sigma takes values between 80 minus mu over sigma and 85 minus mu over sigma. Okay. Okay, so now let's put in the numbers for mu and sigma. Those were 110. And over here, when recall that if you had a general normally distributed random variable, subtracting off its expectation and dividing by its standard deviation gives you the standard normal. Okay. So, and 80 minus 100 over 10 is minus 2, and 85 minus 100 over 10 is minus 1.5. Okay. So then we have, that's the probability that the standard normal lies between minus 2 and minus 1.5. Well, that's the CDF for the standard normal at minus 1.5 minus the CDF for the random normal at minus 2. Well, if you want to convert, that's equal to, this here is equal to 1 minus the CDF at 1.5. And this is 1 minus the CDF at 2. So this would be f at 2 minus f of 1.5, which is 0.0440. We look these values up in the table. Okay, how about we try this? The heights of 1,000 students are approximately normally distributed. The mean is 174.5 centimeters. The standard deviation is 6.9 centimeters. Let's estimate how many heights are less than 160 centimeters. Okay, so we assume that it's normally distributed. So we're asked for heights less than 160 centimeters. So that's the probability that x is less than 160. Okay. So the probability that x is less than 160 is the probability of that x minus mu over sigma is less than 160 minus mu over sigma. Well, if you take a standard, if you take a normal distribution, normally distributed random variable, and you subtract off its expectation and divide by its standard deviation, what do you get? You get the standard normal. So this is the probability that the standard normal takes a value less than 160 minus 174.5 over the standard deviation, which is 6.9. So that's the probability that the standard normal takes a value less than minus 2.1. That's f of minus 2.1, which is minus f of 2.1, which is 0.0179. So you multiply that probability times 1,000 students, 1, 2, 3. So we would say 17, 18 students would have heights less than 167. Skip the moment generating function discussion. Okay. Now, a useful result. If X is normally distributed, it has expectation mu and variance sigma squared. Now y equals ax plus b, that's a new random variable. It turns out that it is also normally distributed, and it has an expectation a mu plus b, a variance a squared sigma squared. Okay. Okay, what happens if you sum two random variables? So x is normal with an expectation mu x and a variance sigma sub x squared. And y is also a normal random variable, and it has a expectation mu y and a variance sigma sub y squared. And supposing that they're independent, okay, this is important. You have to suppose that they're independent. Then the sum x plus y is in fact also normally distributed. Its expectation is the sum of the expectations of x and y, and its variance is the sum of the variances of x as well. Okay, so that's an important result. Now we come to another important application. Supposing that x is a binomial random variable, and then you recall that its expectation is n times p. P was the probability of a success, remember? And the variance was npq. Q was the probability of failure, which is equal to 1 minus p. Okay. And small n was the number of trials. Right. So now as the number of trials goes up to infinity, then the distribution for this new random variable z is equal to x minus np over root npq. That is the standard normal. Okay, in the limit as n goes to infinity. So here's an example. A coin is tossed 400 times. What's the probability of getting between 185 and 210 heads? Okay, so let's see. Yeah, well, we're assuming a fair coin here. Okay. Now, because you're dealing with the right random variable here to use is the binomial. But we're dealing with 400 tosses and a probability of getting between 185 and 210. So we can, because the number of trials, these 400 tosses is big enough, is large, we can actually use an approximation. So the expectation is mu is equal to n, 400, times p is a half, is 200. So we expect 200 H's. The variance is NPQ, which is 400 times a half times a half, which is 100. So the probability that X is between 185 and 210 is approximately equal to, we're approximately using the normal random variable. So that's 185 less than X less than 210. So you take 185, subtract off the expectation, divide by the standard deviation. Less than, well, when you took X minus mu over sigma, you turned X into the standard normal instead. And then this 200, you do the same thing to it. Take 200 minus the expectation 210 minus the expectation 200 divided by the standard deviation 10. Okay, that's the probability then that the standard normal lies between minus 1.5 and 1. And that's the CDF for the standard normal at 1 minus the CDF for the standard normal at minus 1.5. Now we use our table, or we use the online form, and we get that this is 0.8413 minus 0.06668, and that's equal to 0.7745. So that would be the probability, approximately, the probability of getting between 185 and 210 tails. Okay, so that was a brief introduction to the most, well, arguably the most important continuous random variable.